morning, Earthlings! If you follow the channel, you know that we got our greasy hands on an Apollo Flight Director Attitude Indicator, thanks to Patron and collector Richard. It is also known as the 8-ball indicator because of its resemblance with the black billiard ball, but NASA officially called it the FDAI. Two variants were used, one in the command module and one in the LEM. Unlike traditional two-dimensional horizon indicators found in airplanes, this space instrument is three-dimensional. Its display consists of a ball that miraculously rotates around all three axes. It indicates the spacecraft attitude as derived from the inertial platform. The LM FDAI also has 6 needles to indicate roll rates and attitude errors. It is the primary flight instrument in the spacecraft. Our LEM indicator was made by Lear Siegler and is related to another indicator that the firm had previously developed for the F-4 Phantom fighter plane, the ARU-11, which we had restored previously. It's close enough that some parts are shared between the two, and that's why forward-thinking Richard brought us some ARU-11s to be used for spares. Which was a wise move. As we discovered in part 1, our FDAI had quite a storied life. It started service in an Apollo LM simulator, the trainers in which the astronauts practiced. After the Apollo program, it was slightly modified and reused in a space shuttle simulator. But along the way, something dreadful must have happened to it, and it became a parts unit before eventually being disposed of by NASA. In part 1, we opened it up and found many disconnected and broken wires. Many screws were loose or completely missing. Worse, a whole Servo amplifier board was missing. But my suspicion is that this is the tip of the iceberg and that some terrible fault is hiding somewhere that made this unit not repairable, used for parts and eventually disposed of at government auction. As you'll soon see, I was not far off the mark. But before we do anything else, step 1 is to identify and reconnect as many of the loose wires as we can, so we can maybe power it up partially and begin our checkout. So everybody has worked hard on this thing but me. What are your new findings?
Well, the main thing we found was what to do with these 7 loose wires that went to an amplifier board that's now missing.
Mm-hmm.
So I looked at my schematics from the ARU-11 amplifier board and figured out what we need to measure, and then figured out most of the wires, and then cross-checking with the color code in the other ARU-11 board, we think we know where all the wires go.
Okay.
So we're ready to hook up the other amplifier board. Mark pointed out where the 2 broken wires on the power supply board go. So we now think we know where all the mystery wires go. So I looked at the needle for the yaw rate and traced it back through one of these variable resistors to the pins.
Which makes sense, so you would adjust the sensitivity of this thing.
So there's no weird AC demodulation mumbo-jumbo going on. It should be just straightforward, put it in a DC current and the needle moves.
So what Ken is referring to is the demodulator for the needles that is part of the LEM flight instrument. In the real LEM, the needles were fed with 800 Hz AC signals, which amplitude and phase had to be demodulated by the instrument before being applied to the needles. But apparently our modified flight simulator unit has been simplified, and the needles are connected directly to the connector via some added trim pots. They can be actuated by regular DC voltage. This provides us with an opportunity to start with an easy test of the needles before we dive into the far more complicated ball actuation. So you're just setting up for trying just the needles. We start simple. Yeah.
Power supply is on.
Yeah. Okay, here we go. How many volts is that? 2, 3? Nice.
Yeah, there you go. We go up.
Nice.
More.
Okay, so at least part of it is alive.
I don't see very well. Okay, so go down a little. All right.
Do you want to reverse polarity for a moment, see whether we can go down?
Sure. So there you go, fully working FDAI.
Yeah.
everything is bipolar if you switch the wires back and forth.
But then I don't get to show off my HP
Yeah,
equipment.
it works.
There you go.
Mm-hmm.
All right.
Cool.
So that's full scale is 1.8 volts.
One more, and that is one of the big yellow needles. It works.
That's the roll error. That's full scale. Go back down. The other way around. At minus 0.9.
Okay.
Ready?
Yeah, go for it.
Going up. 1.6. Can I go up to it?
Yeah, yeah, go for it.
So right now that I'm at max 2.4.
Because you're on the 2.4 scale on the meter, so
Yeah.
on the
Then go back down.
yeah, go back down and change the.
Change the scale.
scale.
Here.
So is that 0?
That is 0 volts.
Yeah, it's not centered.
Or should we go 16 volts actually?
Yeah.
Let me go here first of all to 0, the 0 position. Okay, and now I'm going up.
It's very satisfying.
What am I here?
About 6.
6 volts. Okay, so I'm at 7 volts. The other way around, and back down. I don't know, but anyway, that's it.
Alright. And of course we couldn't resist to test the flag. This is a caution indicator that's actuated by the 28 volt power and sticks out when there is no power. It's an indication to the pilot that the instrument is not powered on and should not be relied on.
You can have the honors, but
No,
that's okay.
Works. So this is just 24 volt DC, just a
Yeah.
simple magnetic thing.
just so to indicate that it's got power and it's working.
Alright, with preliminaries out of the way, it's time to do our first repairs. We'll also start easy with the broken wire for the front face illumination. It probably failed because of a previous botched repair. The wire had been broken and reconnected after having been simply wire stripped again, which left it too short. It ended up taut and predictably pulled on the connection, eventually ripping it off again. We'll have to properly extend it this time. Note that the illumination itself is a modification for the simulator. The flight instrument had a high voltage electroluminescent illumination like the rest of the control panel. This was replaced by standard low voltage bulbs in the simulator, which probably lacked the high voltage EL supply. Yeah, okay, so we should do the right thing. We should put an extension to this thing, because this is just too short. Yes, yes, perfect. And now I have some slack. The same slack as the other wire. There we go. Alright. There we go. Alright. Clean soldering job. Yeah, if I hadn't put the additional stuff, it would have been all under tension. Okay, so we have that one, then we have the two other one at the back. We also had found two other wires that had been ripped clean from their pins on the power supply board. An easy repair too. Oh, that's easy because the pins, we can remove them. Right, this is our connector. Yeah. Whoop. All right, so that's not going to be too hard, and then there's the other pin. Oh, these are the cleaning ladies. Up. All right, two pins.
Oh, nice.
Oh man, this pin has been bent. This give me a break. So there has been some serious tugging going on. Okay. Oh, interestingly enough, this had been nicked. What happened to this thing? The remnant of the wire is still in there. So we have to try to plug that out. Here we go. I didn't film the entire wire resoldering procedure, but you get a picture. It is now clear that this instrument was a hand-modified prototype. These pins would not be suitable for flight. All right. Here. There you go, repaired. Okay, next experiment was to check the light since we just repaired the wiring. And it's 5 volts, I figured out. And it actually lights up. But out of the 6 bulbs, we have 3 working. So we have 1, 2, 3, 4, 5. And we're missing 6, 7, 8.
Yeah.
Right, we're missing a few. The lights will need some more TLC later, but we got most of the straightforward fixes out of the way. Now it's time for the meaty part of the restoration, the mechanism that actuates the ball and its missing servo amplifier board. But before we go there, I need to explain how the ball servo control actuation works. We had explained it in our ARU11 restoration video, but let me give you a refresher. Assuming that the FDAI ball is similar to the ARU11, each axis should have a motor to spin it around. They are unusual AC motors with 2 windings. The first winding is called the reference winding and is permanently connected to the 115 volts 400 Hz supply. On its own, this winding will not spin the motor. To get the motor spinning, we use the control winding. It takes a much smaller AC voltage, 28 volts max. The magnitude of the control voltage and its phase will determine the speed and the direction of the motor spin. The control voltage is low enough that a small transistorized servo amplifier board can provide it. And that's the board we are currently missing, the one controlling the roll axis. The servo amplifier input signal comes from a control transformer, which is the second cylinder next to the motor. The control transformer is mechanically tied to the ball, which is in turn linked to the motor via a gear train, so everything turns together. Continuing backwards in our schematics, the 3 input windings of the transformer are the electrical inputs to the FDAI. They are connected to the synchro transmitter for the corresponding axis on the inertial platform. Let's assume that the control transformer position does not match the inertial platform position as transmitted by the synchro. An AC voltage will develop at the transformer output proportional to the angular difference between the two. This is the so-called error signal. It will be amplified by the servo board and applied to the motor control winding. This will cause it to spin and move the ball until the transformer is aligned with the inertial platform. At which point the transformer output drops to 0 and the motor stops. This arrangement ensures that the ball always follows the position of the inertial platform. There is one more wrinkle to this though, which is needed to stabilize the servo loop. The servo amp is also connected to a tachometer generator contained in the same package as the motor. The tach provides an AC signal proportional to the speed of the motor. It is subtracted from the error signal. This trick stabilizes the servo loop, preventing the ball from overshooting its final position. Finally, one last detail which will become important. Our motor's control windings have a center tap at midpoint. So the servo amplifier needs 2 outputs, each controlling 1/2 of the winding. In normal operation, these 2 outputs should be out of phase. We have had major trouble with the servo amplifiers during our ARU11 restoration. But this was a blessing in disguise as we became very familiar with them, and they are the same servo boards that are used in the FDAI. So step 1 will be to harvest an extra servo board from the ARU11 spare and transplant it into the FDAI. But since we had so much trouble with them before, we better make sure they work.
Yeah, so when I opened it, I noticed that there was a missing board. I found out in the meantime it's the Servo amplifier board. They are actually related to the ARU11, it's the same manufacturer. We might be able to use the boards here to fix this and make this whole.
Right, and you went specifically after
That's
an
right.
ARU11.
That's right.
That had the very same board, and on the ARU11, as we showed in our previous videos, the boards are inside here.
That's correct.
Whereas on the FDAI,
They're actually inside. They're not an add-on module in the back,
right.
They're actually inside.
So the hope is that we can pluck one from the ARU11 and repair our FDAI.
Yeah, that's right.
So we are ready for the next step of our FDAI repair. I desoldered the extra amplifier from the ARU11, pinned it so we can put little connectors on it, put some input signal on it, and I haven't powered it up yet. As you can see, I just have a little connection board, and the motors are represented by resistors that are buried into there. And then we power the amplifier first, or the stage first, because there are two powers that come to it. Okay, no current drive. Oh, right. Knobs. It's not very symmetric, is it?
No.
I am saturating, so I need to get. Let me wire up an attenuator. It's amplifying very much. Sorry, I need a quick elevator music restart to explain what I'm testing here. Ken had reverse engineered the amplifier during our ARU11 restoration. It's a 3-stage AC amplifier. There are 2 inputs, one for the control transformer air signal on pin 2 and one for the tachometer on pin 3. They are simply added together. The first 2 transistors Q1 and Q2 amplify the input 400 Hz sinusoidal signal until it is pretty much a square wave. This square wave then drives the primary of T1 through the capacitor C6, which provides the needed 90-degree phase shift. The output of T1 then drives the 2 paired transistors out of phase, each connected to their motor winding halves, through the output pins 4 and 6. In order to test the amplifier, we need to power it with 18 volts and put a 400 Hz input signal at about 300 millivolts, not 1 volt as depicted here. I'll replace the motor windings with 330 ohm resistive loads with the midpoint tied to 28 volts. I'll be able to observe the output waveform across these 2 resistors. If all goes well, we should see 2 out-of-phase waveforms when each of the output transistors tie their respective winding to ground. I later found that I made a boo-boo while building my test breadboard and that I put the 220 ohms in place of the 330. That explains why my outputs are not looking quite symmetric in the following, but fortunately, except for having me puzzled a little bit, it didn't have any adverse consequences on the debug. I'm annoyed that it's not symmetric, but I get the same behavior. You know, the turn on,
So
turn off.
how do the transistors feel?
They feel fine. I'm pulling hardly 30 milliamps. So it's fine, and the jiggling here is because my connectors are loose. Yeah, let's bring it. So I could desolder another one, but I have to reconnectorize it. Or we could check one of the other amplifiers. Now that we have this, that's the idea of having the test bench, is that we can pull another amplifier.
You mean one of those, or the ones from?
The one from the FDAI. So we just take it, plug it out, and compare.
A few moments later.
All right, Ken and Richard have taken a board from the FDAI, which has been reworked because one transistor is marked OK. They have X's here and here. So we're not the only one that ever blew up a bad transistor from one of those cars, and ooh, that didn't do what I wanted. What? Didn't do anything, so this is good, this is... Oh, maybe it's my connections. No. I see nothing. I think this one is a no-go. Okay, so that's not so impressive, so I have to pin this one.
So should we take the third one from
I
the
think so.
FDAI?
I think so, from this experiment proves that you might expect them not to work. Alright, so I'm going to, I need to put some connectors on this little guy. I have some pins left over from my Nixie tube projects. That worked perfect for this case.
We have rubber gloves. Oh, here.
Okay. So the one that says OK on it is not OK at all. So let me see if that one works. Okay, that's an amplifier. It does exactly the same thing.
So we'll call that working as intended.
I think so.
Okay.
This is the second board from the ARU11.
Oh, okay.
Reacts the same.
Should we check the third FDAI?
I think so.
Yeah.
I think we might have found why this was a parts instrument. And Richard extracted the second amplifier in his FDAI. And this one is not even hiding it. This says bad, and this says bad also. So I've hooked up the one that's marked bad and expect it to be bad. On. It's not as bad as the other one that's marked OK. It's hardly out of phase, right? So it is bad too. Let me try the third one from the ARU11. Okay, so that's the one from the ARU11, the third one. So the first and the second tested good. Is this one going to continue the trend? Yeah, and it behaves exactly the same way. So you have 3 good ARU amplifiers, you have 0 good FDAI amplifier, which is why it's a parts unit. Now you know.
Okay.
So on the FDAI that doesn't work, they're both marked bad. There's actually only one channel that's bad, and this is the one that has this output transistor. So I'm going to test it, but it could be that the stage before is not symmetric too. So one of the two. So bad transistors goes into the transistor tester. So I have the 2 transistors here from the FDAI that half works. And that's the side that was working fine. It's a fine looking transistor. And there's the side that's not working as well.
It doesn't look that bad.
Yeah, it was still working a little bit. Might not be the whole story. I have replaced the transistor that was suspicious with a good one from my collection. And guess what? I have the same problem, so I didn't fix anything. I see the same problem, which tells me it happens before, and out of the first transistor, it's nicely biased. I get a good sign out, and here I'm starting to see things that I don't like. It's not symmetric at all, which is why I see this really low late turn on. And then if I look at the output of that, it reflects exactly that. So that should be a square wave, and it's not symmetric. I bet you the bias of the second transistor is not right. And I would suspect if I have a bias problem, it's one of the caps that's leaky. And I already can tell you that this one is leaky, because I can show that to you right now. I'm going to remove the signal that's here. I'm going to remove the input signal for a short minute. And My white signal's gone up. Where is it? It's all the way over there. So what's happened is that this gap is terminally leaky, and it's allowing the plus to go right through it. So I have a cap that conducts DC, and I bet you they're all bad. They all leak. And since we have 3 of the other amplifiers come from the ARU 11, exact same part number, we put the good ones in and we move from there.
Meanwhile,
and so news is not that great on your side either.
So while we have the amplifier boards out, Mark suggested we check the control windings for the motor. So each motor has 2 control windings. One motor, the center point of the windings does not seem to go to the 26 volts as it should. So either the winding in the motor is broken, or there's a bad connection somewhere in all these slip rings and tiny wires.
I have flashback of our blue ARU 11. Right
now I'm trying to see if I can trace it to the connector on the ball. And then that would tell us if the problem is in the ball or outside of the ball.
And if it's in the ball, I get to take the ball apart. And which axis is that?
Pitch.
And is that where the amplifier was missing?
No, the roll was the amplifier missing.
Okay, so
if a winding burnt out, we would expect to see open between the 2 windings, which we don't see. Which kind of suggests it's a wiring issue and not a motor issue.
more moments later.
But I measured at the connector here, and so that shows that everything on this side seems to be fine. So it's either the slip ring inside the ball,
the second slip ring, or the motor itself, or a wire. So we have to open the ball to figure out what. Which makes sense, right? Because this is why we get them, because the only ones that NASA got rid of were the ones that were terminally broken or used as parts.
And that would explain why this one has had the amplifier board removed for use somewhere else.
Yeah.
They just gave up on it.
They just stole it. Yeah, and then, yeah.
They gave up on it, but we haven't.
Well, which means I have to take it all apart to go to... Is there any more you can test in that form, or we're pretty much done?
I mean, I can test a little bit more on the connector, but from what I've measured, it seems like it's a problem inside the ball.
So I looked at it under the microscope, and obviously somebody has tried to get into the ball, because there's like half of the screws are missing. Half of the screws for the needles are missing, which you need to replace first. Half of the screw for the front shield are missing. Let's take a picture of everything, because I have to take the 4 needles, or 5. The flag has to be removed. And then I get the shield, and then I can open the ball. And then we'll find why the technician wasn't able to repair this one before you can.
Hopefully we will succeed where they failed.
Alright, I think we'll end this episode on these much needed words of encouragement from Master Ken. This poor FDAI was definitely tossed for a reason. Although we were able to repair its ripped wiring, the 2 remaining servo amplifiers tested bad, and there is an open wire fault deep into the unit. It looks like we are headed for major ball surgery. Well, that didn't sound right. Whatever, see you in the next episode.